Okay, so this is part 5 of the tutorial. I'm going to be talking about running the synthetic tracker. So at this point, we now have images that have been aligned, they've been normalized, and they have also been plate solved. Now, truthfully, the tracker did not require them, it does not require them to be plate solved, but it's just a matter of preference if you want to plate solve before or after. Some people might say, well, maybe I want to find out what's in the information first before I bother with plate solving it, and that's a perfectly valid strategy as well. In this tutorial, I followed the format of alignment, normalization, plate solving. But again, you can do plate solving after the fact if you wish. Okay, that being said, so one thing that's important before you run the tracker, one observation here is the delta time between each exposure. It is saying 2.16 minutes from one exposure to the next. And this is important because it imposes a limitation on how slow an object can move, and the tracker still be able to detect it as movement from one exposure to the next. So what is the limit? Well, you can run a calculator, and you can also just do that by hand. But the simple calculation involves simply saying, what is the target speed in arc seconds per minute? So if we are, in this example, working with main belt asteroids and they move pretty slowly, then I would say something like 0.5 arc seconds per minute. And I have a plate scale again of 1.65 arc seconds per pixel. So I can click calculate. And so with those two parameters, the target would have a movement of 198 seconds per pixel. So that means it will move 1 pixel every 198 seconds. Well, that's almost 3 minutes, which is more than the 2.16 minutes listed in the delta time. So what that means is if an object were moving at 0.5 arc seconds per minute, then this is too small of a delta time from one exposure to the next for the software to notice the object is moving. It would almost appear stationary from one image to the next, because not even 1 pixel has changed in that 2 minutes of time. So there's two ways to solve this problem. One is you can manually open up the directory where you have these images, and you can just simply remove every other image, or you can click on this Exclude button and you say, okay, give it a value of 2, which means it will exclude every other image from the list. Okay, so the images are still there in the directory, but they have been excluded from this list. Now, it's important to note that if you do this technique, it's important to remember to do it every time you wish to run the same data. In other words, if you run the tracker and you save those tracks and you want to revisit them again on down the road, you need to remember that you excluded half of the images so that it operates in the same fashion. So if, for example, I come back to this program the next day and I load my images up, and I were to load up a saved track, then it wouldn't work quite the same unless I were to, again, remember to perform the exclusion. So it might, for some of you who forget, are forgetful, it might be somewhat worthwhile to just go ahead and perform the exclusion of these images in the directory anyhow. But again, this is only really necessary if you acquired these images and you didn't realize that you should have had more delta time from one exposure to the next. So ideally, before you do your observing run, before you do your acquisition of images, you should know ahead of time what kind of target speed you're going to be looking for. So if you want to capture really fast moving objects, near Earth objects, then this exposure is too long, and there's absolutely no need for this much delta time. So again, you do have to spend some time thinking about what's the optimal exposure time and what's the optimal delta time from one exposure to the next. Anyhow, this is a way to, if you didn't set up a perfect imaging run in the first go around, this is a way for you to kind of fix it after the fact. So, okay, I've talked about that long enough, so now let's go ahead and talk about the tracker. So I can kick off the process now, and so again, I just went to Action, Run Synthetic Tracker, and it presents me with a dialog box for a star subtraction threshold. So what this does is it's a way to mask the stars. We don't need them in the image data. If anything, all they would tend to do is produce additional false detections, and we don't want that. So this slider here at the bottom allows me to adjust, and you can see it has quite a lot of travel in it. It can go up to 65,000 is the count there, and I do that to accommodate a wide range of CCD imagers, or CCD and CMOS chips. Anyhow, but as you get closer to the value you want, then you can actually just use the arrow keys. So I can use the arrow key left, or I can use the arrow key right. Anyhow, that lets me get a precise value. And this is a pretty good threshold. That what we're really looking for here, and I'm just adjusting the brightness, what we're really looking for is to ensure that the background has not been masked. So it's good to go ahead and mask the stars, but you don't want to eliminate any of the background level. So so to me that looks great. And you might ask, well, what if the asteroid were as bright as some of these stars? Well, the asteroid is a moving object, so it's not going to be impacted by this. So anyhow, you can go ahead and click OK. The next dialog box is going to ask for a sensitivity threshold. So I'm not going to go into too deep of an explanation on this here, but just to give you an example, if you were to set it to 0, that is way too low of a threshold. That would, first of all, that would produce a huge number of false detections, and secondly, it would take an enormous amount of time to process all the motion vectors. So 0 is way too low. It doesn't matter how many images you have. I would never recommend setting it to 0. Now, if just to start out with, I would recommend try a threshold setting of 35. If you have a lot of images, you could possibly turn it down to 28, maybe even turn it down to 20, for example. So that just gives you an idea of kind of the range you might be able to work with. If you don't have very many images, if you have very few images, I would suggest bumping it up to 40, maybe even 50. But we have right now a decent number of images. We have 40 images, I believe, to work with, thereabouts. I'm sorry, actually we just have 20. We have 20 images because I did the exclusion. So I'm going to say 35 is acceptable, and I'm going to click OK. And the next thing is to determine, do we want to do adaptive or manually specified? So adaptive, that's what I'm going to use in this tutorial. That's part of the blind solving process. Basically, the software has some idea of what motion vectors to try out based on the delta time from the one exposure to the next, and that sort of thing. So I'm going to choose adaptive, and finally it's going to ask me start and stop movement. So start movement, that is how fast it could be, and stop movement as how slow it can be. So again, these are units of seconds per pixel. So 30 seconds per pixel means it will move 1 pixel every 30 seconds. Okay, now how did I come up with 30? Well, again, the exposure times are 2 minutes, and at least for my general rule of thumb, I like to say maybe the object could have 4 pixels of streak. Okay, so maybe it could move 4 times, it could move 25% of this exposure, so that would be 30 seconds is 25% of 120 seconds, or 2 minutes. And finally, for the stop movement, I actually, again, if you're going to try to detect all possible asteroid movement, then you can actually just put in as high a number as you want. I could put in 9,000, for example. The software is smart enough to know that there is a limit, again, relating to the delta time of the exposures. So it's that if you put in something like this, it's actually going to go ahead and stop right at the high end point where that it would no longer see any movement from one exposure to the next. So this is also a good thing to know. Again, if you are trying to image something that moves very quickly, then you can actually dramatically reduce the number of motion vectors by having a really short delta time, meaning that if the delta time is small enough, then the software, it won't have to try out that many motion vectors. So that's just an idea to keep in mind. But for objects that move slowly, like these main belt asteroids, you will need to have sufficient delta time. But in any case, that is what I'm doing here for my start and stop movement. Is I'm saying 30, and I'm allowing the software to determine what a good stopping point would be for the stop movement. Finally, the step size then would be how much granularity we're going to have from one motion vector to the next. So I typically say 0.5 is good for objects moving 30 seconds per pixel or slower. Now, if you have a very fast moving object, say a near-Earth object that moves if it were moving 1 second per pixel, meaning every second it's going to move 1 pixel, then you do need to choose a smaller step size. For example, 0.1. So keep that in mind. If you're doing near-Earth objects, or objects that move very quickly, you need a smaller step size. So anyhow, for this tutorial and this particular data set, 0.5 works great. So as you can see, this results in 52,900 motion vectors. So I'm okay with these parameters, so I'm going to go ahead and click OK. And that kicks off the tracker. So it is now iterating over all those 52,900 motion vectors, and as you can see, it's not going to take forever. It's actually making progress even as we speak. And this is again on my GTX 970 graphics card. It's a 4-year-old graphics card, and I'm even capturing a video while it's running. So it's not too slow. It takes a few minutes, so I'm going to go ahead and pause the recording right now.